So, but in this case, this arose from the fact that the H Hamiltonian, it commutes with J. So we can make the statement that there's a relationship between degeneracy and symmetry. Okay. So, in the example at hand, we have H commuting with J. So we see that the system is rotationally invariant. Thus, in this case, we can ascribe the emergence of degeneracy to the system having some sort of non-trivial, say non-trivial symmetry. So degeneracy, therefore, is intimately linked to symmetry. It's not a very easy statement to make, and I'm not making the most general statement. Degeneracy is intimately linked to symmetry. In particular, degeneracy is related to symmetry, which is generated by a compact group. So rotations are compact. What does it mean? For example, for rotation parameter can have to be between 0 and 2 pi, right? Or in quantum mechanics, 4 pi. Because for fermions, we can have 4 pi. But translation, for example, translation parameter can be -infinity to +infinity. So when the parameter space has a finite volume, such a space is called a compact. The symmetry, the collection of symmetry is called a compact group. You don't have to know what group is. It's just a collection of symmetries. But when the parameter of transformation is, takes value in an infinite interval, then it's a non-compact group. Okay, and the degeneracy is more related to the compact group. Okay. Okay, I think. Okay, any questions?
No questions.
We have about 7 minutes, and I'm not sure if I should.
Could you recommend some basic readings? I don't know if Benny has it, like relations of degeneracy to symmetry. Things.
Which book?
I mean, I don't know whether Benny has anything related to it, but could you recommend?
No, it doesn't. It doesn't.
Oh, okay.
I am not sure which book. Probably, Sakurai.
Oh, okay.
Sakurai.
Sir, I wanted to I didn't get a clear idea how degeneracy is related to the symmetry.
Right. So, you see that this is a statement of symmetry, right? This is something we were discussing, is that if, symmetry means that if you have a state with a certain energy, if you rotate the system, you get to a new state which has the same energy. Okay, so earlier today we discussed this over here. Let me just. Here. So we started with a system, and the system. So we started with a system, and the system was in some state psi, and we did a rotation of the system about some angle alpha, through some angle alpha about some direction in space n. Then the state changed to psi prime, where psi prime is related to psi by a unitary operator u alpha n, where this operator is given by this thing. And we said that rotational invariance means that the energy of the state that we started with and the energy of the state that we ended up with have the same energy. And that statement is given here. The expectation value of the Hamiltonian in the transformed state is equal to the expectation value of the Hamiltonian in the original state. But the original state is related to the transformed state through this relationship, U acting on the original state, and then U dagger acting on the broad. So this left-hand side becomes this. Now, although we chose psi to be our initial state, there was nothing special about psi. We make the statement that this has to be true for any psi. It doesn't matter if a system is rotationally invariant, it doesn't matter what state we are in. If you transform it, its energy doesn't change. If that is true, then this equation must be true for whatever psi we choose. That means that it has to be a statement that is true as an operator statement. So we can get rid of the psi's here. And then what we do is that we choose alpha for mathematical convenience to be a small number, a small rotation. Now, because U has the form of e to the power minus alpha n hat dot L, if I take alpha to be small, I can do an exponential, a series expansion where the first term is 1, and then I get I alpha n dot L, and I ignore the higher order terms. So if I do that, then this is what U becomes. And U dagger becomes exactly a similar expression, but this minus sign is replaced by a plus sign. And then we look at this equation up to order alpha. And I skipped a step, but I can do it now. Then this becomes 1 minus I alpha n hat dot L multiplying H, and then 1 minus 1 plus I alpha, and then it is n dot L is equal to H. Now, if I expand this, I get 4 terms, 1, 2, 3, 4 terms. So the first term will cancel is just H, and that'll cancel the right-hand side. The fourth term is of the order alpha squared, so we can ignore it. So there are 2 terms of order alpha, and these 2 terms differ by a sign. And therefore, these two terms form this commutator. But in this commutator, alpha was an arbitrary angle, n was an arbitrary direction. Again, for this to be true in general, then it has to be true for every component. So we can get rid of the alpha and get rid of the n, and we can write this in terms of component, and that's how we get statement. That the statement of rotational invariance means that the Hamiltonian will commute with the operator of the angular momentum operator. Okay. So now, if I have a state which has some energy h, then because h commutes with L, even if I have, if I apply the raising or lowering operator on that state, it'll have the same energy. So all the eigenstates of L will, in the given multiple will have the same energy h. Okay? Which is what I showed here, is that if I started with some state, and then, so it doesn't matter if it's J or AL, it's the same logic. If I apply J minus to this, so if the energy eigenstate of this is E0, if I apply J minus to that state and then apply H to it, I get the same energy eigenvalue equation. That means that these two states have the same energy eigenvalue. And that has to do with the fact that I've used the fact that H and J, they commute. And therefore here, H acting on J minus and the state is equal to J minus H. This is the key. Okay, this is the key. Okay, Wadia?
Yes, sir.
Okay. Any more questions?